If you've ever built a RAG agent before, you'll have encountered situations where the agent can't answer questions accurately or it hallucinates an answer. This is all because of the lost context problem. And in today's video, I'm going to show you what this problem is and two new techniques that you can use to get around it to improve your retrieval accuracy and reduce hallucinations. The best way to explain this problem is through an example. So here we have a document on the city of Berlin, and this is a Wikipedia article. In a standard RAG system, we would need to chunk this document. In other words, we split it up into segments. So if we look on the right-hand side then, if we were breaking down this document per sentence, so a chunk equals a sentence, then we would end up with these three chunks. Now in reality, you wouldn't necessarily chunk per sentence, but this is good just to demonstrate this problem. The first chunk speaks to Berlin being the capital of Germany, the second refers to its population, and the third sentence talks to how it's one of the states of Germany. Only the first chunk actually mentions the word Berlin. And as you can see highlighted there, in the second sentence, Berlin is referred to as its, and in the third sentence, it's the city. So clearly for the second and third chunk to make sense, it needs to have the context of the first chunk. It needs to understand that the city is referring to Berlin and its is referring to Berlin. So unfortunately, that's not how standard RAG works. These three chunks will be sent independently into an embedding model to create vectors, which would then be stored in a vector store. And because they're sent in independently, they're in complete isolation of each other, and they've lost the context of the paragraph and of the document. And the real issue then is, if you were to query this vector store with the word Berlin, this first chunk would most likely return a very high score because Berlin is specifically mentioned. But Berlin's not mentioned anywhere in the second chunk here, so you could get a very low score, and the same for the third. And this is a lot of the reason why you might not be getting complete and accurate answers from your RAG system, because a lot of the important information is just not being retrieved. And worse still, it can result in hallucinations because there may be unrelated chunks that actually have a higher score that are then returned, and then the LLM will faithfully generate a response of what is effectively unrelated information that was retrieved. There are lots of ways to mitigate this problem, a number of which I've already covered on this channel. And in this video, I'll be going through two new techniques you can use in n8n, namely contextual retrieval and late chunking. If you don't know what RAG is, then I recommend checking out some of my other videos where I dive into the basics in a bit more detail. But in a nutshell, when the AI is asked a question, we retrieve the most relevant pieces of information from your knowledge base and feed those to the AI so it can generate a more accurate answer. That way, the LLM isn't limited to what it saw in its training data, and instead it can pull company-specific, up-to-date information on the fly. So before we jump into our first technique, which is late chunking, let's ask the question, what is chunking? And as I mentioned earlier, chunking is where we split a document into segments so that it can be processed by the RAG system. So here I have a really long PDF document, and if we put this through a chunking algorithm, you can see the color-coded segments that have been created. And then there are different chunking strategies that you can use that'll define the boundaries of these chunks. You can increase or decrease the number of tokens or characters. You can have overlap, for example. So there is a lot of ways that you can chunk. Unfortunately, there isn't a one-size-fits-all strategy. It does depend on the type of documents that you're bringing in. Late last year, Jina AI published a new approach to chunking, which is called late chunking. And that's to have contextual chunk embeddings using long context embedding models. And I've taken this strategy and brought it into n8n and built out a RAG pipeline where we can ingest documents and embed and upsert them using this late chunking technique. But before going through the workflow on n8n, let's talk through how late chunking actually works. So with the standard RAG approach, we're essentially chunking first and then we're creating the embeddings. So if we take that Berlin example that we looked at earlier, that's this document, let's just say that's the paragraph. We create the chunks of that, which are the sentences, and then we push those sentences into an embedding model to generate vector embeddings. And then those vectors are stored in a vector database where they can be then queried in the future to retrieve similar results. That's your standard RAG approach of chunking first and then embedding, losing the context. With the late chunking approach, we're actually embedding first and then we're chunking. And all of this is made possible thanks to long context window embedding models. So similar to how the latest LLMs have very long context windows, Llama 4 for example has 10 million tokens, the context window lengths of embedding models is also starting to increase. So within this approach then, you would load up your entire document, or as much of the document that can fit in the long context window as possible, into an embedding model, and then every token within that document will have a vector embedding created for it. But that all happens at the same time, so it's all within the context of the document. And from there then you use your chunking strategy of choice, be it chunking into sentences, into paragraphs, fixed length, recursive character splitting, at which point you have segmented your document into bite-sized chunks, and then instead of sending those chunks into the embedding model, we're able to identify which vectors that were previously created actually are associated with that text. So for the first paragraph, it's these vectors, second paragraph, it's those vectors. And because all of those embeddings or those vectors were created at the same time with the entire context of the document, you're no longer losing the links in between the sentences and the paragraphs. So back to the Berlin example, even though Berlin is not mentioned in that second or third sentence, the actual tokens will reflect that Berlin was in context. And from there, there's a technique used called pooling or aggregating, where those vectors are averaged out to represent the chunk, and then they're stored in the vector database. So you still have a single embedding to represent the chunk, the same as standard RAG, except because these are pooled across these tokens, they more accurately reflect the text. As I mentioned, late chunking is only possible thanks to long context embedding models. And if we look at the embedding leaderboard on Hugging Face, you can see the max tokens that these embedding models actually support. So the likes of Mistral and Quinn's embedding models can support up to 32,000 tokens. That's a good deal shy of the millions of tokens that LLMs can support, but it still means you can fit a lot of text into context when actually creating those tokens. In my n8n workflow, I'm going to be using Jina's embedding v3 model, which you can see there, and that supports a maximum of just under 8,000 tokens. So onto the workflow, I'll be testing out both late chunking and contextual retrieval against a simple RAG setup that I have here. So here I'm fetching the document from Google Drive, and then I'm using a recursive character text splitter and OpenAI's text embedding 3 small model to generate embeddings, and then all of those are upserted to the quadrant vector store. So it's pretty fast, and you can see the vector store here with 645 points for that 170-page document. To implement late chunking in n8n requires a little bit of manual work. The problem here is that you can't add custom embedding models. So if you look at the list on the right-hand side here, Jina AI is not one of them. And also it's not possible to pass custom parameters to embedding models. With late chunking, you need to pass a flag to enable that, which isn't possible with a lot of these. If you'd like to get access to these advanced RAG workflows, then check out the link in the description to our community, the AI Automators. What we're doing here is we're fetching a file from a Google Drive folder. This is the same file I use in a lot of my RAG videos. It's the Formula 1 technical regulations. It's 180 pages long, and there's a lot of text to be processed. From here, I'm looping through the files because this is being triggered based off new files being added to the Drive folder. I'm then downloading that file so it's accessible by n8n. And then depending on the type of file, I'm extracting the text. So if it's a PDF, I'm using the extract from PDF node, which is essentially picking up the binary data from the previous node where I downloaded it. Google Doc, for example, it'll come down this track and convert it to Markdown. Then I need to check the size of the text. So what I'm saying here is if the text length is greater than 30,000 characters, then we need to come up this route and just create a quick summary of the document. So the rationale here is we can't actually load up all 170 pages into this embedding model. While it's a long context embedding model, it's not that long. So we do need to split this document. So if we split this into 10 segments, for example, I want to index a quick summary of the document in each segment so that it actually has the context of what the entire document is about. So that's what's happening here. Then that file splitting occurs. All of this was generated by ChatGPT. But essentially what we're doing here is we have a split text into chunks function, and then we're just creating chunks of the main document that are 28,000 characters long, which equates to around 7,000 or 8,000 tokens, which is the max tokens of the model itself. And then from there, we're looping through these really large chunks, and we're carrying out a more granular chunking. So if we click into this, we're aiming for a chunk size of 1,000 characters with the chunk overlap or a sliding window of 200 characters. And we want the overlap boundary to be on a word, so it's not cutting off words. And we have various separators like new lines that it can actually be triggered off. And then there's various functions for getting the overlap boundary, and then the actual recursive splitting function. So the reason this is all JavaScript is that n8n does have chunking functionality, but it's embedded in their vector stores. They're not actually standalone modules. If you type in split here, you can see there are text splitters, but they're all subnodes of the vector stores themselves. You can't have them inline in your flows like I need here. And the reason I'm not using the native vector store in n8n is that it currently doesn't support this type of late chunking, so I actually have to build it out manually. Again though, all of this code was generated by ChatGPT and just a back and forth just to get it working. From there then, we aggregate all of those granular chunks into a list, as you see here, and then we have another code node which adds that document summary if the entire document doesn't fit into the embedding model's context window. So that's what's happening here. From there then, the list of chunks that we created are sent in a single shot to the embedding model. We're hitting the embedding URL and we're passing this body where we're selecting the model that we want to use. We're indicating that late chunking should be enabled on this. We have truncate set to true just in case we've strayed past the actual limitation of the model itself. Task is set to retrieval.passage, which is recommended in Jina's embedding documentation. You can see the various options here for downstream tasks. And if it's a RAG style implementation, they recommend using retrieval.passage when indexing and retrieval.query when actually inferring. And then all of the granular chunks are passed in as the input and are embedded at the same time. We're using a quadrant vector store here. So we then need to upsert all of those vectors into our collection and quadrant. So I'm simply just creating a body here where I generate an ID and output a data structure that the quadrant API requires. Again, ChatGPT generated a lot of that. And then I upsert it to quadrant. So I'm hitting my collection, which is this one, and then I'm just sending in that body that I created in the previous node. Okay, so let's save it and let's test it out. And what I'll do is I'll just delete the quadrant collection that I have. And I'll create a fresh one. So this is our collection. There's no points present. Okay, and let's test workflow. So we've downloaded the file, extracted the text from it. We then go to summarize the document. And from here, then we're now looping through those large chunks. We're creating the more granular chunks, generating the embeddings with Jina, and then upserting to quadrant. And if we refresh here, we can now see all of the various vectors. So this clearly would have been a lot easier if n8n supported custom embedding models with their vector stores. That's just not possible at the moment. So that's finished. Now, if we jump into the generate embeddings with Jina, and if we look at any of these runs, these large chunks, in the body, you can see that we have passed all of the chunks in a single go to that endpoint. And then in the response, we're getting data. And if we close that, we can see that there are 28 items. So we passed in 28 chunks, we're getting back 28 vectors. And that's then what's essentially upserted to quadrant. Okay, so let's test it out. So let's ask the question, do the aero parts on an F1 car have to remain still? Okay, so that's gone to the vector store. And we have a response, which looks accurate on the face of it. I've had to manually build out the fetch from vector store because n8n doesn't support custom embedding models. But when executed by the agent, it's just hitting these two endpoints. So you can see the query was here, which was then sent into Jina because we need to generate the vectors for the query so we can find similar results. So that's what we got back. And then we queried quadrant, which has returned the top 10 results for that query. We have all of the various scores, along with the payload of the text that can be then sent back to the agent to generate the response. Now, if we compare that to our simple RAG setup that I have here, if I ask the same question, and yeah, it's a similar enough result. Let's try with another question. So what parts make up the engine's turbo system? It's broken down 5 key parts, which is reflected in the chunks that we are getting back. We are looking for the top 10 results. That could be increased. We could have re-ranking in place. So there are ways to improve this. But if I just ask that to the standard RAG interface, and let's see the quality of answer we're getting back. It's a less fleshed out answer. It's only talking to 3 of the components. So it possibly isn't retrieving as wide an array of chunks as was returned by the late chunking process. And I think that's the thing about evaluating these techniques versus a standard RAG inference. You do need to have your own evaluation framework and understand what good looks like. And then you need to compare it against different techniques to see which one actually scores the highest for your actual use case. Within the documentation for this approach on Jina AI, they have carried out some quantitative evaluations based off the BEIR benchmarks. And interestingly, what they found is that the relative improvement of retrieval results increases dramatically the longer the document is. And I think that makes sense because the longer the document, the more context there is to lose. So next up is contextual retrieval with context caching. This one was introduced by Anthropic at the end of last year. And it's a really interesting idea because it leverages the long context window length of large language models instead of embedding models to actually provide context to each of the chunks. Now that might sound a bit confusing, so let's go through it here in a bit more detail. So as I mentioned before, with the standard RAG approach, we take a document, split it into chunks, send it into an embedding model to create vectors independently, and then that's all stored in a vector store. So with contextual retrieval, it's a bit different. So you take your document and then you split it into chunks, but instead of sending it into an embedding model, you send it into an LLM. And you also send in the original document. What you're asking the LLM to do is to analyze the chunk in the context of the document and provide a little descriptive blurb on how that chunk fits into the document. So that gives you back a one-sentence description. And from there, then you add that descriptive blurb with the chunk and you send that into the embedding model, which produces the vectors. From there, then you can save that to the vector database. And because it has that one-sentence description, you're not losing the context. If we take the Berlin example again, with that second chunk, the descriptive blurb could say, this chunk is in reference to Berlin. And then it says, its population is X. So with the expansion of context window lengths for LLMs, I think this is a hugely powerful approach. The main issues we're going to have with this, though, is the time it takes to ingest documents, which you'll see in a few minutes, but then also the cost. Because if this document is 1 million tokens long, then you'll be sending that large document in for every single chunk. And this is where prompt caching kicks in, where you can dramatically reduce the cost of sending in that large document each time. So let's run through the workflow. So it's the same again. We're fetching the large PDF document, getting the file, extracting the text, and we get to this point here. So from here, we need to estimate the token length. Again, it's just simple JavaScript, and it's a rough number that we're getting. But the reason is we're going to be using Gemini 1.5 Flash for this. So even though Anthropic actually released this technique, you don't have to use Claude Sonnet, for example. You can use any LLM that has context caching. So I'll be using Gemini, and within Gemini's system, files need to be larger than 32,000 tokens to actually cache them. So that's why I'm actually estimating the token length here. And then if it's large enough to cache, so I'm saying if it's greater than 35,000 tokens, give me a little bit of wiggle room, then we come up here, we're encoding the file. It needs to be encoded into base 64, and then we send it for context caching. So that's this node here. We're hitting the cached contents endpoint, and then with the credentials, we're sending in this body where we pass the entire file encoded in base 64 here. And interestingly, you also pass in the system instruction. So here I'm just saying you are an F1 expert. And for these cached files in Gemini servers, you can also pass in a time to live. So here I'm saying it's 3600 seconds, which is 1 hour. And you don't really need this to be too long. It just needs to be long enough for you to actually get the entire document ingested in the first place. So from here then, we have another custom chunking node, again, for the reason that there's no native text splitters in n8n outside of the subnodes. And what we're looking for here is chunks of 1,000 characters long with a sliding window of 200 characters. And then this brings us down to this looping section here. So initially, I didn't actually have a loop. I just ran it all through, and I quickly hit rate limits within the LLM, because here, if you don't use a loop, we have 600 odd chunks. So it's going to hit the Gemini endpoint 600 times in really quick succession, and you're going to get rejected at some point. So instead, I'm using the loop over items function in n8n, and I've set a batch size to 10. So we're going to hit it 10 times in quick succession, and then allow it time to breathe, and then hit it 10 times again. And that's what's happening here. So here we're enhancing the chunk. We have created a prompt, so you have the document within the context cache. Please give a short, succinct context to situate this chunk within the overall document for the purpose of improving search retrieval of the chunk. Answer only with the succinct context and nothing else. So this text came straight from Anthropic's paper, and it's listed on this document, and I'll leave a link for this in the description below. That's what you see here. Within this prompt, I'm actually passing it the cached content ID, because we've just cached the file on Gemini servers, we've got back an ID, we need to then reference that ID when we're actually generating this descriptive blurb. So that's all there. So then we hit Gemini 1.5 Flash, which is really cheap and has a long context window. So it should be able to take the entire document that we previously cached, and we're passing in that prompt. And from there, then we have our descriptive blurb, and then we just simply create the chunk. So it's what we get back from Gemini 1.5 Flash, and then it's dash the chunk. At this point now, we have the chunk that we can then upsert to our quadrant vector store, and then we're using OpenAI's text embedding model here. You do need to set a text splitter. It's already split, it's already chunked. So I've just set this to 100,000 as a chunk size, just so that it doesn't actually chunk again. And then that's it. That's going to upsert the 10 chunks, and then I go back through the loop and go again and again and again. So now let's run it and see it in action. So we'll delete out our collection on quadrant, and we'll create a fresh one. So there we have it, 0 points. Okay, and let's run it. So it's estimated the token length. It sent the file for caching, and if we dive in here, you can see that's the actual ID. So we're getting the cached contents ID. Then we've created the chunks, so 612 chunks based off this kind of custom function. And you'll see the chunks don't currently have any context yet. So we then dive into the loop, and we loop with that batch size of 10. We're creating our prompt, and then we call Gemini with caching. then this is an example of a response we're getting. This chunk is from the introduction section of the 2025 Formula One guidelines. And I think that's why this approach is so cool. The chunk starts with, this chunk defines the CC plane within the context of the regulations. Or this chunk describes the required datum points for F1 cars. So you really are getting the context of the chunk, which should definitely reduce hallucinations when you're actually generating responses off the back of this. So it's a really cool approach, I think. And interestingly, I have just hit a rate limit, even with this batch size of 10, as you can see there. Service is receiving too many requests from you. So I'm on tier 1, 2,000 requests a minute, so I'm definitely not hitting that. I think the tokens per minute is possibly what I'm hitting because it must be including cached tokens in that. So I'll reduce this to a batch size of 5, let's say, and let's start it again. So you will have to play around with the actual batch sizes and the rate limits because you are literally calling the LLM for every single chunk. So the more documents you have, the heavier this is going to be. And there is clearly a cost associated with this as well. From Anthropic's paper, they did carry out some quantitative benchmarks, and they did see that the top 20 chunk retrieval failure rate was reduced by 35%. And if that was combined then with the re-ranking model, so they use Cohere in this example, they actually reduced the failure rate by 67%. So clearly, while it's a more expensive approach, it should definitely result in higher quality embeddings. It is the tokens per minute that I'm actually hitting here. The quota value is 4 million. And if you look at the actual document, it is 133,000 tokens. And from looking at Gemini's documentation around context caching, standard rate limits apply and token limits include cache tokens. So I've updated this call to retry on failure, and I'll set it as 15 seconds in between a failure. That way it should be able to get past that 4 million tokens per minute constraint. Okay, so that's running again. And even with the retry setup, I've still hit a throttling issue. And if I look at Google Cloud's console here, you can see where I'm hitting the limit on the number of tokens per minute. So I'll need to dial this back a little bit just to stop it redlining, as you can see there. So I think probably 25 chunks a minute will get me under the 4 million. So I'll change this batch size to 25. And then I'm actually just going to put in a wait. I see what the problem is. You can't actually set a wait between tries of longer than 5 seconds. So here I'm setting it as 15 seconds. If I save and then if I double click it again. So that's why I'm hitting these errors. I can't get past 5 seconds there. So I could increase the max tries. Can you leave that at 10? And you can't go past 5 on the max tries either. So yeah, we're definitely going to need a wait facility, I think. I'll set this at 30 seconds and see do I hit these throttling errors again. Okay, so I've sent in 25 chunks, which should be around 3.5 million tokens, including what's in context cache, and send it in the next batch. So I think we might be on track with this approach. Because essentially these nodes are taking about 30 seconds and then we're waiting for another 30 seconds there. Yeah, that's ideal. We're holding steady at the 3.3 million tokens mark. So that should succeed now based off that new technique. So you would need to play around with that to keep it under the rate limits of whatever model provider that you're using. This thing is taking so long, I've left it running and got myself a cup of coffee. So this is clearly not scalable if you have a lot of documents to process. We're keeping well under the limits here, but Gemini shouldn't include cache contents in their actual token allocation. It's ridiculous. You can see on the right hand side that the vast majority of tokens being processed here are cached. So from looking at the numbers, we're going to chew through around 69 million tokens on Gemini. The vast majority of them are cached, which is significantly cheaper than if they weren't cached. And so the total cost here will be around $1.30 to generate these chunk descriptions that we use to enhance the chunks. So whether that's good value or not, I think probably depends on your use case. If you only have a few documents and you want really accurate retrieval for, let's say, a chatbot, that might be fine. Whereas if you have millions of documents, it's going to be way too expensive and it'll take forever to actually process it. With the late chunking approach, to use Jina AI's embedding model, I needed to sign up to their 1 billion token pricing plan, which costs $20 a month. But with that, you get access to all of Jina's products. And we use their deep search and their reader quite a lot in our automations. But of course, there are other long context embedding models that you can use, such as Mistral or Quinn. I'll leave a link for the leaderboard in the description below as well. And we're done. 612 chunks processed and all upserted to the Quadrant Vector Store. It took 27 minutes, which is incredibly long for a single PDF, albeit a long PDF. And we can see our 612 points in our collection. And as I mentioned, the chunk descriptions are brilliant. And this is a perfect example where there's real kind of technical details in this chunk with formulas and just kind of random numbers. And the description here is super helpful in actually grounding all of this kind of technical data in the actual context of the section in the document. So let's test it out. So we'll ask our question about, do aero parts on an F1 car have to stay still? And that actually looks like a better answer than the last two. We're still only returning the top 10 results, but there does seem to be a little bit more detail in that. Let's try this question. What parts make up the engine's turbo system? And that is definitely more thorough than the last two as well. We're getting 7 different elements. And from looking at the chunks that it returned, I think it's definitely picking up elements of what's in these descriptions, because sometimes in the description it gives a list of elements that are actually being discussed in that section of the document. Really interesting. If you'd like to get access to these workflows so that you can test them out in your own systems, then check out the link in the description to our community, the AI Automators, where you can join hundreds of fellow automators all looking to leverage AI to automate their businesses. Not only will you get access to all of our templates and workflows, but we have a packed schedule of events where you can join myself and Alan on technical calls where we actually work through automations that members are working on in real time. And as well as some pretty advanced n8n workflows, we also have an n8n masterclass to really build up your core skills. Check out the link below. We'd love to see you here. Thanks for watching, and I'll see you in the next one.